Hello again, everybody. We are going to take a look at section 7.7, day 2 today, dealing with the power properties of logarithms. So you'll notice that your guiding question today, how does the power property of a logarithm work? And then we're going to utilize that as we start working through problems on this today. So now let's say we have something that deals with our product property that we dealt with yesterday, such as the following. Let's say we have log base 2 of 10 times 10 times 10. Now keep in mind that that product of 10 times 10 times 10 is all with log base 2 in front of it, okay? Well, think about how the product property works here. Recall from the previous assignment, you were working with the product property that says that if you had a log of a product, you could write it as an addition of logarithms. Now think about that for a moment. So that would say log base 2 of 10 plus another log base 2 of 10 plus another log base 2 of 10. Now notice how many of those log base 2 of 10s do you have? Okay? You've got one here, you have another one here, and another one there. So notice that I can treat this in many ways similar to if I had something like, let's say, x plus x plus x. Now think about this for a moment. If I did x plus x plus x, this is something you would be familiar with. You could add those together and you could say 3x. Well, I can do the same thing with my logarithms. I just have to look at this visually and say, okay, I've got 3 items that are the same that I am adding together. 3 items that are the same that I'm adding together. So you'll notice here, what's acting like my x is the entire log base 2 of 10. So I can look at this and I can think, okay, I have 3 of those. So just like I said, x plus x could be set as 3x. Well, here's x plus x plus x. I'd have 3 of them there. I can argue that if I do log base 2 of 10 plus log base 2 of 10 plus log base 2 of 10, I can write that as 3 times log base 2 of 10. Just like over here when we had x plus x plus x, we could write it as 3 times x. Now, we already know that when we deal with 3 times x, we don't need to list the multiplication symbol. Well, we get to do the same thing here. So I can say that this is 3 times the log base 2 of 10 in this manner. Now, you might be wondering, why am I looking at this? Well, let's look at this a little bit differently, okay? So look at 10 times 10 times 10. Besides writing it as 1,000, what would be another way that you could write it? We could look at that instead of writing 10 times 10 times 10, or instead of writing 1,000, could we write it this way? Log base 2 of 10 to the 3rd power. Now keep in mind here, I don't necessarily need the parentheses here. And in many times when you take a look at the textbook, they are not going to list parentheses around them. Now, I want you to take a look at the 2 items in blue now. Okay, so log base 2 of 10 times 10 times 10, I can write as log base 2 of 10 to the 3rd power. When I did the expansion using the the product property, I ended up getting 3 times log base 2 of 10. So let's make a connection here. Instead of having to do all of this work to get to this result, what could I say from here to there? What happened? it's like the exponent was allowed to move down and become a multiplier in front of the logarithm. And that is exactly what this property is. Okay, so this is what is called the power property. And so what it's allowing me to do is it's allowing me to rewrite things. If it's got a power, I can move the power down as a multiplier in front of the logarithm. So take a look at this one. Let's say I've got log base 4 of 7 times 7 times 7. So you'll notice I could make this times 7. It doesn't matter how many 7s I put here. Let's say I make it so I got 5 of them. I can rewrite 7 to the 5th power here, so I can call this log base 4 of 7 to the 5th power. But now here's the neat thing. Instead of having to do the product property on all this and write log base 4 of 7 plus 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 log base 4 of 7, I can write it as 7 to the 5th power first. And the beautiful thing is that I can move the exponent down as a multiplier. So I can write this as 5 times the log base 4 of 7. Now, I know that some of you are probably thinking, well, okay, Mr. Varsh, big deal. Where is that going to come into play that I might need it? Well, we're not going to see it yet in this particular section, but in section 7.5, you are going to be solving exponential equations, where that variable is going to be up here, but we're going to run into a dilemma where I can't change bases and make them match. Okay, so that's what's coming in section 7.5, but that is where the power, no pun intended here, of the power property is going to have a very, very key role. So what you're going to be seeing on the problems that are coming here is you're going to be working with that power property as we work forward here. So essentially, in a summary here, before we start doing examples, is that the power property states the following. That if I have some log base b of any other base that I have, doesn't matter, m to the power of x, so to speak, what I can do is that I can rewrite it moving that exponent down as a multiplier. So it would allow me to write it as x times that log base b of m. All right, so that is where we are going to be working then today, is on this situation. Now we do have to keep in mind, everybody, that we can do this in both directions. So in other words, I can go from the log base b of m to the power of x and move the x down as a multiplier, but I also have the opportunity to go the other way. That if I've got a multiplier in front of a log base b of any number, or whatever it is, I can move it back up as an exponent. So in other words, this property will work in both directions for us. Okay, so we do need to keep that in mind. So let's look at a couple of quick examples of that. Let's say that I've got let's go log base 3 of 16 to the 5th power. Okay, so how can I rewrite that one? I can bring the 5 down front, and I can write it as 5 times the log base 3 of 16. Now, again, I'm putting a multiplication symbol in here. That is not something that is going to be required of you. You can do it, no problem, but we definitely want to make sure that we don't write this 5 on the back side. We might misinterpret that as a log of a product then, where it's a scalar or a multiple that's being multiplied to the logarithm itself. So I don't want to put this 5 on the back side. That would be a common mistake. and it would lead to a bigger mistake later on. We want to make sure we put that down as a multiplier in front of the logarithm as we do this, okay? How about this one? Take a look at this. How about we give log of 15 to the third power? Look at this one. What's the base? In this case, it's not listed, but it would be base 10. So I still get to make the same move. So again, I get to take the 3, multiply it, again, in front of the log of 15. All right? So that is how this power property is going to work for us. So as we start looking ahead at some examples, they might ask us to do a little bit more simplification. But again, we can look at this and say, well, there might be other ways to get it done. But just like in section 7.4 day 1, even though there might be a different way to get things completed and they'd be mathematically correct, we want to stick with the intent of what the directions are saying in the problem. So when you take a look at example 1, you'll notice that it says express as a product and then simplify as possible. So when we take a look at these, again, there might be different ways to simplify it, but we want to stick with the intent. So here we've got log base 2 of 32 raised to the 6th power. Okay, so again, the intent is to use the power property. So on this first one, what can we do? We can move the 6 down, and we can write it as 6 times that log base 2 of 32. Now, in this, they're going to say, okay, keep simplifying if you can. So I'm looking at 32, and I know that I could take that and I could write that as 2 to the power of 5. So there is a little variance you can do here. But if I make that move next, what we want to recognize out of this is that in this particular case, when I change to 2 to the 5th power here, now I can apply a different property that gets me done with it. So keep in mind that I've brought the 6 down as a multiplier in front, but I should recognize this as a pattern that log base 2 of 2 to the 5th power is just the 5. So what happens is now I'm going to bring my little 6 down here. Again, that's like a little brother, a little sister here going to the mall with you. 6 times 5, then I can say my final result is 30. Okay? So again, the intent here is that we're using that power property to write this as a multiplication first. Okay? So take a look at example B. In example B, in this one, we have log base 8 of 4 to the 20th power. All right, so give this one a shot real quick, then we'll come back together. Pause the video. When you're ready, restart and move on. In part B, first move again, we're going to move that 20 down front as a multiplier, so we can say 20 times the log base 8 of 4. Now, in this case, when I take a look at log base 8 of 4, I'm going to run into a problem here because I can't rewrite 4 as base 8. And I can't really rewrite 8 as anything else unless I convert a form. So in this particular case, this would be as far as we would take this particular problem. Now, do keep in mind that I could simplify this a little bit further if I did a different route of things. Okay? But that is, again, not the intent. So when you get to something like this where we cannot simplify in this at this point, we would leave this alone as its answer right here. Okay? So that's why the directions are saying simplify if possible. All right? Okay, so take a look at part C. Okay, so in part C, we have log base 3. Make sure I'm writing that right. Log base 3 of 10 to the 4th. Okay, try it. Pause the video. When you're ready, come on back. First move, just like we did before. We'll move the 4 down. Write it as a multiplier in front of the logarithm. So it would be 4 times log base 3 of 10. In this particular case, there is nothing more we can do with this because we cannot rewrite log base 3 of 10. We can't write it any other way to make it simplify any better. So this would be as far as we can take it. Okay, let's look at part D. In part D, you have log base 5 of 25, and that's raised to the second power. All right, same thing. Pause the video, try it, come back when you're ready. In this problem, we can actually do a little simplification. Now, again, multiple ways we can do this, but keep in mind the intent. I'm going to move the 2 down as a multiplier. So that would allow me to then write 2 times the log base 5 of 25. From here, I should be able to recognize that 25 would be 5 squared. So now I would be taking 2 times log base 5 of 5 squared. So as we saw before, log base 5 of 5 squared is something we can simplify immediately and just say is 2. But again, don't forget our little brother, little sister coming along here. 2 times 2 then is a final result of 4. Okay, so that's the type of stuff you're going to see with some of those. Now, so you already know when a base and the value you are taking of the logarithm are the same, they can undo each other. And they give us the exponent as our result. That's exactly what we saw right here. Okay, so when you see in your next slide, we have log base 2 of 2 to the 5th and log base 10 of 10 to the 4th. Each of those answers would turn out to be 5 and 4 respectively, following the same exact pattern that you're seeing right here. So when we see that further, you're going to see some examples that are following that. And again, that's the power property just being used in a different way. You're already set with a same base situation. So when you take a look at example 2, where we're asked to simplify these expressions, these are going to go a lot faster. So like if I have log base 3 of 3 to the 11th power, I'm essentially going to get the 11 right away here, but we're going to look at it a little bit closer. Now, you've seen that. We dealt with that particular property earlier on in the quarter, or earlier on in the unit. But watch this. I could still apply the power property. So I could bring the 11 down and write it as 11 times log base 3 of 3. Now, this is not an incorrect move, but in the end of it, this is going to be more work than we need to actually apply. Because what is log base 3 of 3? It's 1. So what happens is even though I can apply that power property here and move the 11 down, this is a situation where I'm always going to generate a 1, and I'm just multiplying it with the exponent, so my final result is just the exponent itself. So what we're essentially doing then on these is you're just working with a property you've already seen. Look at the next one. We have log base 3 of 81. Well, how can you rewrite 81? We can rewrite that Again, you'll kind of notice that we're using the same kinds of numbers over and over so that we're not having to keep calculating new results here. 81, we have seen many times already, is 3 to the 4th power. So notice again, the power property, I could move the 4 down, but I get back to log base 3 of 3. I don't need to take the time to do that now. Log base 3 of 3 to the 4th power will just be the 4. Okay? Taking a look at part C. Do part C real quick. The answer in this case is just going to be the 0.9. Okay, I'm not going to actually run through that one, but you should see here it's log base 10 of 10 to the 0.9 power. So all you're going to have is the 0.9. Okay, very, very quick, very, very efficient here. And it's going to save us that extra step. I don't need to do that. I can look at it by just getting the same base here, and then it's the exponent that becomes your result. Now, inverse properties are going to work in the same manner. So again, what we're setting up here a little bit is where we're going to be going in the next section. So we're working with the properties today, but then these properties are going to be what is going to get used in section 7.5 when we start solving equations here. So when we take a look here, now we're looking at an inverse, so they're asking us to simplify. Now notice that in this case, we have what? We have 5 times the log base 10, excuse me, is that base 10? Base 5 of 10. All right? So what's going to happen in this particular property is we're essentially looking at inverse operations again. So here, if I have 5 and it's raised to an exponent, okay? So my base is 5. I'm raising it to an exponent of log base 5 of 10. Well, the same thing is going to happen here is that if an exponential will undo a logarithm will undo an exponential, they work back and forth. So what happens if I see 5 to the log base 5 of some value, what I'm going to get out of that is just the 10. Take a look at the next one. We have 2 to the log base 2 of 8x. In the same exact manner, 2 to an exponent of log base 2 to whatever value I've got will give us just the value. Okay? So what this means is that if a logarithm can undo an exponential when the bases are the same, an exponential will undo a logarithm when they have the same base as well. So as we work forward, there's reasons why we need some of this, is because we run into situations where sometimes our calculator isn't going to work as well for us, okay? So here's a situation that we've got. If you're looking at the next slide, you'll notice that it says scientific calculators. Now again, this is not dealing with your iPad calculator. The iPad calculator has been now advanced a little further than your scientific calculators. But this is something we do need to take a look at because when it comes to an MCA exam, when it comes to ACT, where you're not going to have the iPad calculator in front of you, we have to have a workaround of a situation here, okay? So scientific calculators will use logarithms, but they are only designed to work with base 10 or base E. Now, we haven't touched on base E yet. That's coming, okay? So the problem is that the calculator cannot calculate anything other than those two bases, okay? So in other words, on a calculator, so on a scientific calculator, what it cannot do is that it cannot calculate something like log base 4 of, say, 38, okay? I don't have a way to input base 4 because the calculator is designed only to work in base 10 or base E. Now, base E, when you see that, E is a natural base. It's roughly about 2.61 or 2.718, excuse me, 2.7, okay? So the calculator can only work in those two bases. But I have good news. Watch this. There is a property that is called the change of base formula. Now, we're not going to sit here and prove it here, but there is a way to get these to work. So what I can do with this in what's called the change of base formula, okay? So this is very, very nice. What we can do is we can change our base. Okay, so you notice that in this particular case, the way the logarithm's written, it's written in base 4. Well, the change of base formula will allow us to change it to any base we choose. So, check this out. I could actually change to something that works on the calculator, base 10 or base E. Now, because we haven't introduced the natural base E yet, I'm going to stick with base 10. So what this would allow me to do is that this change of base allows me to switch away from base 4 and switch to base 10. Here's how it works. Instead of saying log base 4 of 38, what I get to do is the following, is I can rewrite it as a fraction. Okay, now don't get worried about the fraction because the goal here is to use this on a calculator. I'm going to change my base. So what I'm going to do is I'm going to do log base 10 of 38. That's good. Let's try that again. 38. And I'm going to divide it by log base 10 of 4. Now that makes it very nice to go to my calculator. Okay, so I can now type in log 38, division bar, log 4, hit my equal sign, I've got my result. Okay, now a way to see how this kind of works, let's say we do something that we recognize. Okay, so what we're doing is we're essentially applying this property, is in a very general sense, is that if I have log base B of, let's say, M, okay, what it allows me to do, and now this is in summary, so this will work for any situation you want. I can change my base, which says that I could go log base A of M divided by log base A of B. Now you might be looking at that and thinking, okay, well, why would I ever think of using something other than 10 or this base E that I keep mentioning? Well, let's say you couldn't use a calculator on something, but they are numbers that I could recognize. Okay, like this one. Let's say we do, I don't know, let's go log base 16 of 4. Now, the issue here is that our base is 16, and the value that I'm working with is 4. If it was the other way around, then I could manipulate my 16, but I can't in this position. So what the change of base formula would allow me to do here is that I could look at this and say, hey, I've got 4 and 16. I know those are both something I can write in base 2. So I could say log base 2 of 4 and divide it by log base 2 of 16. Now what that allows me to do here is now I can manipulate the 4, I can manipulate the 16, and now I can simplify. 4 being what? 2 to the second power. So I could now say log base 2 of 2 to the second power, log base 2 of 16, 16 being 2 to the 4th power, log base 2 of 2 to the 4th power. Well, from a previous piece, what do these release as? 2 and 4. So essentially, I can reduce that, and I can say that the final result then would be 1/2. How's that for something kind of neat? Now, again, you're not going to have to do that kind of thing all that much. And again, keep in mind, we learned another way to do that as well. We looked at that and we said log base 16 of 4, we could just say is y. I could convert its form. And now I could convert here 2 to the 4th power to the y power, 2 to the 2nd power. This would be 2 to the 4y power is equal to 2 squared. Well, notice what you have. You have 4y is equal to 2, y is equal to 1/2. So again, you'll notice multiple ways around this. So what the change of base can do is it can make it so I don't have to convert form, even though I can. Okay? So keep that in mind as we start working forward. But again, most of these are going to be dealing with situations where you need to get to a calculator that you can use them, not necessarily the iPad calculator we had you download. So having this change of base formula is very, very nice. So again, we might want to box that off. This is called the change of base. Okay, so change of base formula. It is becoming more and more obsolete as technology continues to move forward. But again, there are times where we might find that that is a very helpful thing. So, as an example, take a look at log base 32 of 8. Pause the video and try it real quick. It's just like that log base 16 of 4 that we looked at. Okay? Log base 32 of 8. See if you can do it. Pause the video. Come on back. Okay, so in this particular case, again, I'm going to look at the change of base formula. And in this case, I think I'm going to go to base 2. Log base 2 of 8 divided by log base 2 of 32. Now, could I have done any other base I wanted to? Absolutely. We'll take a look at that in a moment. I'm going to do base 2 here just so I can see that I get a nice rounded value. But then what I'll do is I'll pull out a calculator and we'll see what it does there. So like if I switch to base 10. All right, so log base 2 of 8. I can write 8 as 2 to the 3rd power. (32) I can write as 2 to the 5th power. So again, what happens here, log base 2 of 2 to the 3rd power, power property, lets me say 3. Log base 2 of 2 to the 5th will be just 5, and that'll be our result. Now, if I were to do this on a calculator base 10, okay, so again, I could do the same thing. I'll just do this over here in purple. If you were to type this into your calculator, in fact, just type it in, okay? So if I changed it and I said log of 8 divided by log of 32, where I don't have to manipulate the 8 in the 32 here, I'm going to find that I'm still going to get a result here. Now, the calculator in most cases is going to automatically default to a decimal. So if you type in log 8 divided by log 32, you would find that your answer would come out to be 0.6. Well, what is 0.6? That's 3/5. Okay? So again, that's how nice the change of base formula is going to be. So there are a couple of other examples there that you're doing the same exact thing, where you're just going to type it in and calculate. Just stick with base 10 and you're good to go. Okay, so we're going to move on to the final example here where we're taking a look at the idea of the logarithmic scale. Okay, so again, logarithmic scales are used when we are dealing with very, very large numbers. Really, we're looking at numbers that we cannot even fathom in our own mind. A prime example of that is the earthquake. Okay? Now, you've all heard of the earthquake scales. You've heard that they say like 7.5 on a Richter scale. Well, how is that any different than, say, 6.5 on a Richter scale? Okay? So that's where a logarithm comes in. It's also kind of the same way that we do with our hearing, is that decibels are done based on logs as well, log base 10. And so the higher the intensity, the louder it is, or the harder it is on your ears. Okay? Now, a case in that, just before we get started with this example, so you have an idea, you've all been by those vehicles driving along the road, you stop at a stop sign, and you can literally feel the vibration of the car because they've got those big bass amps in there. I mean, it literally vibrates. That is the intensity of the sound. But again, you think of the person that's in that vehicle riding, think how hard that is on their ears. It's loud, but it also is really causing a lot of vibration. Intensity and decibels. It's like standing next to a vacuum cleaner as compared to when it's off. Okay? Vacuum cleaner is louder than when I speak. And so that's an intensity. It's an amount of pressure that's being forced on your ears. Okay, so we're going to take a look at an example here, though, that's dealing with earthquakes. Okay, so you'll notice that the tsunami that hit parts of Asia in December of 2004, it was formed by an earthquake with a magnitude of 9.3. Okay, so let's think about that. That's huge. Now, when you look at that and you think 9.3, well, that's not a real big number. But we got to take a look at the amount of energy that is released in what they call ergs. Okay, so you'll notice that you're being given the model here is that the magnitude, okay, so where this number is coming from, this magnitude m, is equal to 2/3 times the log and base 10 of that amount of energy in ergs divided by 10. Oh, look at there. It's a negative, or excuse me, 11.8 power. Okay? Now you think of 10 to the 11.8 power. That's pretty massive. Now I want you to just think about that for a second. Let's just say 10 to the 11th power. Well, that's going to be what? That's 10, that's a 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros behind it. We're looking at 11.8. It's almost 12 zeros. Okay? That's massive. I mean, we're talking a million, a trillion. We're talking 100 trillion here. So we're looking at massively large numbers that we just cannot fathom in our own mind. So when we look at this, that's why they generate a scale that we can recognize. So in this case, if I look at this, we're looking at a magnitude of 9.3. Now, here's a neat thing. We can actually figure out the energy here by solving for E. Now, this is a lead-in when we start getting further on in section 7.5. Now, don't overthink your process here. Your logic and your first instinct will be correct here in how to handle this. The first thing we're going to do is we're going to divide by 2/3, or maybe better would be is to multiply by 3/2. Okay? So again, if I do that, I'm just going to be multiplying by 3/2. Okay? So I'm going to get a result here. Let me pull out a calculator real quick. If you've got your calculator, go ahead and do it. I'm going to have to type mine in here a little bit. I don't have my actual phone up here. Okay, so if I do this here real quick. All right, so when I calculate, and again, I want to be a little bit careful on my answer here, because I do have to keep in mind every time I hit my equal sign and write a rounded answer, I'm introducing more and more error. So I know that I'm going to have a little error here. So I'm doing 3 divided by 2 times 9.3. And I come up with 13.95. That one worked out okay. All right, so we get 13.95. That worked out fine. That is now equal to log base 10 of e over that 10 to the 11.8 power. Now, this is where we're starting to look at how do we actually solve for the e. Well, because I'm in log base 10 here, if I were to change the sides, let's say I just swap these over, and I rewrite its order as this. I'm just flipping sides. So I'm writing log of e over 10 to the 11.8. Okay, I'm going to treat that together. That's equal to that 13.95. Now, you might be looking at that going, okay, Mr. Varst, why? Well, because I have a logarithm here, I can change its form to an exponential. So in other words, I'm dealing log base 10. Let's convert with our right-hand visual rule. Or excuse me, counterclockwise visual rule. I can now say the following. Now I know I'm running low on a board here, but what this would allow me to say is the following. 10 to the 13.95, ooh, that's a big number, is now equal to e over 10 to the 11.8 power. So notice that what it's getting at is now I can really get at the e because I'm no longer in logarithmic notation. I'm now in exponential notation. But now remember, these are very, very, very large numbers. So notice, to get e by itself, it's being divided by this 10 to the power of 11.8. So I'm going to move this over here so I got a little more room. So I now have 10 to the 13.95 power, which is massive already. We're talking almost 14 zeros behind a 1. And we're saying it's equal to e divided by 10 to the 11.8. A situation there where I have almost 12 zeros behind a 1. Now, I can't even fathom those numbers. But look at the fact I have to solve for e. If I do this, I have to multiply both sides by 10 to the 11.8 power. Holy cow, look at this. I'm going to be multiplying 10 to the 11.8 power times 10 to the 13.95 power. That's extremely large. So by the time I get done here, I'm now multiplying like bases. I get to add those exponents. So I'm really doing 10 to the 11.8 plus 13.95. Whoo! Look at the size of that. Okay, so now I'm doing 11.8 plus 13.95, and I'm coming up with 25.75. We're talking almost 26 zeros behind the 1. We can't even think of that. We can't even fathom that, which is why they come up with a Richter scale to say, hey, we can at least give it some sort of a number that we can recognize. 9 is bigger than 8, 8 is bigger than 7, and so forth. Now you think of most average earthquakes, you get a little rumble maybe. We've never had it here in Minnesota that I know of. I've never felt one. But even a massive one, like what happened during the World Series back years ago, 89, 90, somewhere in there. You were all not alive yet. But it happened in Los Angeles, and it tore things down, and that was a magnitude of 7 something. And that was considered massive. This is much larger yet. Okay? So that is why we have the logarithmic scale, is so that we can at least try to get something that we can wrap our mind around. Okay, so you will have some examples of that in this assignment as well. So as you're working forward here, everybody, keep in mind, we will hit some questions within our live feed when we get to that. But at this point in time, I'm going to let you go on the power property, change a base formula, and now you got a little bit of application that ties to it. Your first instinct is most likely the correct one. So stick with that first instinct. Have a great day, everybody. Stay safe, and we'll see you on the next live feed.